So, the second lecture of the moment of inertia is the polar moment of inertia. Now, polar moment of inertia, that is the moment of inertia possessed by a body when it rotates about a axis which is perpendicular to the plane of the body is called the polar moment of inertia. For example, let's say one disk or one area is there. Now, when it rotates about its perpendicular axis, body, the axis is this one. When we calculate the moment of inertia about this perpendicular axis, then it is called the polar moment of inertia. Now, thing is that difference. This is the body. This is called Ix, here or here, Ix. This axis is Iy. What is polar axis? This axis. When body rotates about this axis, or it's sometimes called when body rotates about its own perpendicular axis, that is called the polar moment of inertia. This axis. Now, the mathematical significance of the polar moment of inertia is because if you consider a mass dm or dA, छोटा सा area dA, let it is the area moment of inertia, consider a small area dA, then the distance is r, it is rotated about a radius r about this axis. Any point it is rotated in the radius r. Then the IP is r square dA. That is the mathematical formula. Ixy square dA, Iyx square dA, IP r square dA. Now this is the significance only. Here one important thing is coming, one is called the perpendicular axis theorem. Perpendicular axis theorem. Perpendicular axis theorem. Let's say this is our reference x-axis, this is the y-axis. Consider a area or mass dA, let's say area moment of inertia dA. Now the polar moment of this polar axis is this one, IP or IZ. I cannot show it, so I can draw like this, IP or IZ axis. Let the radius is r, it is lies at a distance r. That means this is the axis, this IP, I cannot show it, this is the axis and it rotates in this axis with a radius r. Now you understand the concept. Then I can say my IP according to the mathematical formula, what is this one? R square dA, R square dA. Integration. Now say this formula, this is the area dA. Now it is rotated a radius r. This radius is r. It is rotated about the axis. This is the IP axis. Same diagram. Now when it's rotating, it is create a circle. Now circle, let's say this is the any time the x, this is x, this coordinate is y. That means the coordinate of dA is x and y. Then I can easily write r square is x square plus y square into dA. Because you know the equation of circle, if this coordinate is x and y, then x square and origin is 0, 0, 0. If origin is 0, 0, because this is the origin only, then x minus 0 square plus y minus 0 square, that is simply x square plus y square is equal to r square. That is the equation of circle. That is integration of x square dA plus integration of y square dA. Now y square dA initially just recall the previous lecture, that is Ix, plus what is x square dA integration, that is Iy. Therefore IP is equal to Ix plus Iy. Because it is quite difficult, rather than the circle, Other figure, rectangle, how the mass is rotating, because this mass is rotating, it is very difficult because you cannot get the integral limit. So the perpendicular axis is the solution to find out the polar moment of inertia of a rectangle or a circle or a triangle. Circle, it is quite easy because circle, all the elements rotate in a particular radius r. This is called the perpendicular axis theorem. If you know the moment of inertia of x-axis and y-axis, then simply adding these two, you can find out the moment of inertia axis, which is perpendicular to both x and y-axis. This is called the perpendicular axis theorem. Now let us take few numeric examples and numericals. Polar moment of inertia of a circle. First example. Polar moment of inertia of a circle. Polar moment of inertia of a circle. If I am telling a circle, now you understood about which axis I am trying to find out which perpendicular moment of inertia, about this axis. About this axis. Polar moment of inertia about this axis, not ix and iy, this axis. So ip, polar moment of inertia ip is equals to r square ta. This can be derived by using our formula. So consider a ring. Consider a ring at a distance, let's say q, and its thickness is dq, and the radius is, let's say, r. I can take r because I am fixed the r for the entire radius of the circle. That's why I am taking q and dq. Otherwise r dr ले सकते थे, लेकिन उसका पूरा radius r है. So let the in between radius consider a distance q, radius q. We consider a ring whose thickness is dq. Then the area of the string can be given as 2 pi q into thickness dq. Ip is equals to, now integration of r square, here for this element r is q square, 2 pi q dq. Understood why r I have reserved for the radius of the circle, and dq, the q varies from 0 to r. That equals to 2 pi comma, so integration of q to power cubic power dq, that equals to 2 pi q4 by 4 0 to r. That equals to 2 pi r4 by 4, that is pi r4 by 2. Now this is the answer. Moment of inertia of a polar moment of inertia of circle, that is pi r4 by 2. Alternately, if we, because a proof is given, then this way only you have to prove. Now little bit here, we know ip is equal to ix plus iy. That is the polar moment of inertia of a circle is polar moment of inertia about x-axis plus y-axis, ix plus iy, perpendicular axis here, that equals to 2ix. Because in a circle, since it is symmetric about x-axis and y-axis, its ix and iy are same. Previous lecture we already discussed. That is 2ix. That means ip is equals to twice. What is the value of ix? Ix, previous lecture, if you derive that RB strip like derived किए थे, there we derived it is pi r4 by 4, that is equals to pi by 2 r4, which is same as this one. because pi r4 already we derived. Now this is the just clarification of the perpendicular step, but this part is the derivation. This is the application of the perpendicular axis theorem, these two lines. Similarly, if Ix, Ip, if you derive like this, anybody ask you Ix, instead of going that derivation is a little bit complicated, simply you can say Ix is equal to Ip by 2 pi r 2 by 2 pi r4, that is the value of Ix and Iy. Reverse you can do. This method is the quite easy. Example, polar moment of inertia mi of a rectangle about its CG. Polar moment of inertia of a rectangle about its CG. That means which axis you have to find it a moment of inertia? Above the CG axis, which is perpendicular this axis. So this is, let's say, A, this side is B, x-axis, y-axis. Now I find out the polar moment of inertia passing through the CG. This one, this axis. Can I write Ip is equals to Ix plus Iy? Polar moment of inertia Ip is equals to Ix plus Iy, perpendicular axis theorem. That is equals to, because here you cannot derive it, integration करके we cannot calculate this one. Ix is equals to Ix ABQ by 12 plus BAQ divided by 12. Ix and Iy already we derived this one, that is AB by 12 A square plus B square. Some other example, book numerical 1 or 2, let me check, because instead of rather than the circle we cannot calculate the other figure by derivation, because यहाँ पे स्ट्रिप लेके r में इंटीग्रेट नहीं कर सकते, because all the masses are different radius. यहाँ पे r है, इसका radius है, यहाँ पे कोई mass नहीं है, that's why we cannot calculate it up. There we have to take the help of the perpendicular axis theorem only. One, two question, your book question, 1 or 2, let me take question. This is the example of book question, your Timoson book. Calculate the moment of inertia of an isosceles triangle. This is the isosceles triangle. Both the sides are same, isosceles triangle. About its apex. Polar moment of inertia about apex. That means the point is at the apex. The axis, polar axis is this one. About the apex. Now if I draw two lines here. This is the x-axis. This is the y-axis. Then I can say my Ip is equals to Ix plus Iy. Polar moment of inertia about this Ip axis is same, is equals to Ix plus Iy, perpendicular axis theorem. Now we have to see what is the value of Ix and Iy. Ix, that is the, the triangle is A, B, C, and this point is, let's say, D. This side is B, this height is H. Ix, it is the moment of inertia of triangle ABC about its apex. That is equals to Now I think you can follow the lecture note of the class 1. The formula for this one is BHQ divided by 4. There we have derived. Follow the class note of the previous lecture. IY is this line. IY is this line. Can I write IY is 2 into moment of inertia of triangle ADC or ABD, both are same, that's why 2 I have written, about its base. Am I right? Because now this half of the triangle, if I draw y-axis, this one is like this. This is the y-axis. Half of the triangle I am doing. A, D, C. This one is B by 2 and height is H. 2 into, like these two triangles are there because both are isosceles. 2 into moment of inertia of triangle ADC above the base. Now base is AD. That is equals to 2 into moment of inertia of the triangle is BHQ by 12 D. But here B is, base is H. Height Q. Height is B by 2. B by 2 whole cube divided by 12. 1 by 12. That is 6 into 8, 48. HBQ divided by 48. I think I'm right. So IP is equals to IX plus IY, that is BHQ by 4 plus HBQ divided by 48. This is the answer. If you can take in something common, BH by 4 can be taken as common, so it left H square plus 12 BH common, B square divided by 12. That can be taken as common answer. Here also you will get the simple questions, not by using the formula only the circle we can integrate it derive to, that is pi r 4 pi 2. Other things I only using the perpendicular theorem we have to find it out. No other way is there. Find the polar moment of inertia of the shaded portion shown in the figure. The shaded portion is composed of, it is a square of side R and it is a quarter circle, circular arc or quarter circle of radius R. We have to find out the moment of inertia of about this one, about this axis, polar axis. So here I can say my IP is equals to IP1 plus IP2, or I can say polar MI of a square, R and R the square, about its corner, one of the corner point, it is corner, that's a IP1 plus polar mi of a quarter circle it is, quarter circle about its center, IP2, and your IP, something mistake is there. What is that? Not plus, minus this portion, square minus. Now IP1, what is that? That is the polar moment of inertia of the square about this point, about this axis. Now if I say this is the x-axis, this is y-axis, then polar moment of inertia of a square about this axis is ix plus iy. IP1 is equals to ix plus iy. Ix plus iy. So what is ix? Polar moment of inertia of the square about this axis. That is, already we use this formula, otherwise in the class note it is abq by 3. But here a and b both are same, so it is a4 by 3 plus, in this axis square both sides are same, here baq by 3, ba are same, that is again a4 by 3, that is 2a4 by 3. Ix, Iy, that is the moment of inertia about the base of the square, moment of inertia about the base of the square. abq by 3 over x square, same thing because a, b are same here. Similarly, IP2, it is simply the polar moment of inertia of a circle. Thus now we calculated, that is the pi r square 4 by 2, but it is quarter circle, so it is 1 by 4 of a polar moment of inertia of a whole circle, that is pi r 4 by 2. Formula, you can refer the formula, that is pi r 4 divided by 8, that is pi a4, sorry little bit, 2 r 4 by 3, because here a is equal to r, formula I put it, a is equal to r. So IP is equals to IP1 minus IP2, that is 2r4 by 3 minus pi r4 by 8, r4 can be taken as common, 2 by 3 minus pi by 8. So you can compute it, a little bit computation I done, I think. Yeah, it is 0.2739 r to power 4 answer. So this is about the polar moment of inertia. Only one formula you have to remember, and other formulas by Ix, Iy formula from the previous chapter you can do. Some other numericals might be there in the book also. 4-5 numericals are there in this entire chapter, polar moment of inertia, that I already did in the class note. You refer the class note for the other 1-2 numerical, because 2 and 3 I have already solved here.